Hello, my name is Shahriari, and this is a lecture in a series of lectures on undergraduate abstract algebra based on my book, Algebra in Action. The subject of this lecture is the group S4 and one of its subgroups, D8, dihedral group of order 8. A group is a non-empty set together with an operation. This operation must be closed and associative. There is an identity element, and every element has an inverse. Examples, the dihedral group of order 8, the symmetries of a square, and S4, the symmetric group of degree 4. I will remind you what those things are. The purpose of this lecture is to show that S4 has a copy of D8 inside it. Or in the jargon of group theory, we want to show that S4 has a subgroup isomorphic to D8. I didn't use the word prove because I'm not formally doing that yet. At some point, we will have better tools to be able to say these things more succinctly and more reasonably. Let me remind you what D8 was. There's a whole video on dihedral group of order 8 and the symmetries of a square. I urge you to watch those. You can think of a square sitting in a frame. You take it out of the frame, do things to it, put it back. That final way of putting it back is called the symmetry of a square. I'm thinking of a frame so that you don't take a square out and then rotate it 20 degrees and want to put it back because then it won't fit. One thing you could do with a square is do nothing. If you're lazy, you just do nothing. That's a symmetry. It's not an interesting one, but it's a symmetry. All rotations are going to be counterclockwise. So 90-degree rotation counterclockwise is a symmetry. 1 goes in the place of 2, 2 goes in the place of 3, 3 goes in the place of 4. That's one symmetry of the square. Well, you can do that twice, and that's the same as a 180-degree rotation, or 3 times, and that's a 270-degree rotation. And in fact, R0 is the same as 360-degree rotation. We also can do other things. We can flip the square about an axis, a horizontal axis, going right down the middle. A reflection about that horizontal axis is also a symmetry, as is a vertical reflection, a reflection about an axis that's vertical and goes down the middle of the square. D is the reflection about the main diagonal, the matrix diagonal of the square, and D prime is the other reflection. These are the only symmetries of a square. A square has 8 symmetries. If you focus on, say, 1, where can it end up? It can end up in one of the 4 squares. And as soon as you decide where that 1 goes, then you have 2 choices. You can either flip the square so that 1 is in the back or not, and the 1 is in the front. You have 4 times 2, 8 choices for a symmetry of a square. The set of symmetries of a square are these 8 things: R0, R90, R180, R270, H, V, D, and D prime. So far, I've got my non-empty set, but there's more to it. I also have an operation. I can do 2 symmetries in succession. You might do H, a horizontal reflection, followed by an R90. And if you do that, then that's also a symmetry. In fact, because we had a complete list of symmetries, it's one of those. It happens to be D prime. It's the reflection about the non-dominant diagonal. We write that as R90H equals D prime. When we write R90H, we're thinking of function composition. H is going first and it's going to be on the right-hand side. H and then R90, but we write that as R90H and we get D prime. We also came up in the video on the dihedral group on D8 with an alternative algebraic notation. So instead of R90, we decided to call it A, and instead of H, we decided to call that B, the horizontal reflection. Then the elements of the group D8 are A, that's the R90, A squared, that's AA, that's the same as R180, A cubed is R270, B is H, and AB is D prime. A squared B is V, and A cubed B is going to be D. We also have E, which is identity, and we have these relations. A to the 4th, that means you do R90 4 times, you get this identity. If you do H twice, you get identity. And BA is not AB, so this product is not commutative, but BA is A cubed B. If you have any word in A's and B's, you can then reduce them into A to a power, B to a power. Yet another way of writing this, maybe the best way, is that dA is the group generated by A and B. All that means is that you start with A and B and write any kind of a word you can from them, any succession of A's and B's, 5 A's, 2 B's, 3 A's, 5 B's, and so forth. And that's what D8 is. And because we have those relations, A to the 4th equals B squared equals E and BA equals A cubed B, those words can then be reduced to one of those 8 things. Writing things as generators and relations is not always easy, but in this case, we can easily see that this is D8. Now let's go on to S4. What is S4? We had one video on one-to-one onto functions from any set to itself, and then another video on the symmetric group. Bracket n stands for us for a set with n elements, 1 through n, and Sn is going to be the set of one-to-one onto functions, bijections, from bracket n to itself. So these are one-to-one onto functions, but you can also think of them as permutations of 1 through n. Sn is called the symmetric group of degree n. It has n factorial elements, because how many places can you move 1 to? You have n choices. After you do that, regardless of the choices you make for where you put the 1, you have n minus 1 choices for 2, and then n minus 2 choices for 3, and so forth. So there's n factorial ways of making permutations or one-to-one onto functions from bracket n to bracket n. S4 is the group of permutations of 4 things, 1, 2, 3, 4. It has 24 elements. And in group 3, we like to use the cycle notation to write them. For example, some elements of S4 are these guys. That first one, 1, 3, 2, 4, it's a 4 cycle. It's a cycle of length 4. 1 goes to 3, 3 goes to 2, 2 goes to 4, 4 goes to 1, and that's a one-to-one onto function or a permutation. This other one is a 3 cycle. It takes 2 to 4, 4 to 3, 3 to 2, and 1 is fixed. And this one is a 2 cycle or a transposition. Switch the place of 1 and 3, and 2 and 4 both stay put. I'm talking of them as permutations, but I'm using the cycle notation. How do you multiply elements of S4? You use function composition. You have 2 one-to-one onto functions, 2 bijections. When you compose them, you get a bijection. For example, how do you multiply 1, 3, 4? That's a 3 cycle. By 2, 3, 4, which is another 3 cycle. Thinking of function composition, that means 2, 3, 4 goes first. You do this one-to-one onto function, the 2, 3, 4, then you do that other one. How do we do this? Go to the video on Sn, but very quickly, we start with 1 and say, well, where does 1 go? We have 2 functions that we're composing. You've got to start with this one, the 2, 3, 4. What does that do to 1? That one fixes 1. So 1 goes to 1. Now what? Now you have to apply the second function, the one on the left, and say, where does 1 go now? 1 goes to 3. 1 goes to 1 and then goes to 3. So 1 goes to 3. So far, we know that when you compose these 2 functions, 1 goes to 3. Where does 3 go? We might wonder about 2. We haven't decided that, but because we are on our roll here, 1 went to 3, we want to see where 3 went. So we go to the first parentheses here, which is the first function. Where does 3 go? 3 goes to 4. Now, where does 4 go? 4 goes back to 1. So 3 goes to 1, and to show that, we close the parentheses. We've got that 2 cycle. 1 goes to 3, 3 goes to 1. They're switched. Am I done? No, because I haven't decided where 2 goes. So I go back to the first thing that I haven't decided, and that's 2. Where's 2 going? In the first function, 2 goes to 3. In the next one, 3 goes to 4. So 2 goes to 4 in the product. And where does 4 go? 4 goes to 2. And in this second function, 2 is fixed. So 4 goes to 2, 2 goes to 2. So 4 goes to 2, and I'm closing the parentheses and I'm done. This group has 24 permutations of 4 things, and you combine them in this particular way. Now let's try to think of D8 as a subgroup of S4. One of the purpose of this lecture is to look at D8 from a different perspective, to realize that you can think of the elements of D8 as permutations and in fact as elements of S4. You might be comfortable thinking of D8 in one particular way, but what you have to do as an algebraist is to be able to look at it at a specific object from different points of view and say, I need to think of this as a group, or I need to think of this as symmetries, or as permutations, or as generators and relators. And each one of those will give you different kinds of insights. To think of symmetries as permutations, you have to label the corners of a square, 1, 2, 3, 4, which is something that I did actually when I was defining it, because I wanted to show you what the symmetries do. I labeled the corners. But here, if you want to think of them as permutations, you've got to focus on those corners. Every element of D8 actually permutes those corners. In the jargon of group theory that we will actually be using quite a bit later on, we say that D8 acts on the corners of the square. It takes the corners of the square and permutes them. But more than that, multiplication in D8 corresponds to multiplication in S4. If you think of each element of D8 as a permutation of the 4 corners, then when you do 2 of the symmetries in succession, then you will get a new permutation. But the point is that that's the same as the way we combine permutations. The way we combine symmetries in D8 is the same as the way we combine permutations in S4. We can think of D8 as sitting inside S4. I'm saying these things somewhat informally. Later on, we'll have the language of homomorphisms, isomorphisms, and group actions, and we will prove this very clearly, but with more jargon. I'm trying to whet your appetite for what's to come. R90, for example, is the 90-degree rotation counterclockwise. I can think of that in terms of how it permutes the corners of the square. 1 is going to the place of 2, 2 is going to the place of 3, 3 is going to the place of 4, 4 is going to the place of 1. That's one way to think of it. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. You could have thought of it differently. You can say, look, this picture you have here is giving me a one-to-one onto map. 1 is going to 4, 2 is going to 1, 4 is going to 3, 3 is going to 2. That happens to be the inverse of this element. It would be fine if you said that A is that permutation. R180, what is that? 1 goes in the place of 3, 3 goes in the place of 1, 2 goes in the place of 4, 4 goes in the place of 2, if you're thinking of it as permutations of the corners. Or you can think of R180 as A times A squared. If you think of it that way, and we already had that A was 1, 2, 3, 4. If you multiply those together, you get 1, 3, 2, 4 again. And the reason is this, both times doing the same thing. We are repeating A, and A is the permutation 1, 2, 3, 4. If you do it twice, that's the same as multiplying 1, 2, 3, 4 by itself. This is what I meant by saying that the multiplication in D8 and the one in S4 do correspond. We also have H. H is switching the place of 1 and 4 and switching the place of 2 and 3. And so that corresponds to this permutation in S4. You can't get all permutations of S4. For example, just switch the place of 2 and 3 without doing anything to 1 and 4. That's just not possible. So not every permutation of 4 things is a symmetry of the square, but the symmetries of the square are permutations of 4 things, again, by focusing on the corners. The elements of D8, we can just write them down now. So identity is the one that fixes 1, 2, 3, and 4. I like to keep calling it E. Most people call it just 1, and that's perfectly fine. A is 1, 2, 3, 4. A squared is 1, 3, 2, 4. A cubed is 1, 4, 3, 2. B is 1, 4, 2, 3. AB is 2, 4. A squared B is 1, 2, 3, 4. And A cubed B is 1, 3. And when I say it's is, there's nothing written coming from the sky that says that this is the only way that I can represent them. I could, for example, switch around the place of the labels, and then I would actually get different permutations. This is just one way of representing D8 as elements of S4. In this way of doing it, D8 is these elements. These are permutations of 4 things. And this is a group. D8 is a group. It's closed. It's associative. There's an identity, and every element has an inverse, but it's sitting inside a bigger group, S4. And such a thing is called a subgroup. That will be something that we will talk about in a future lecture in some detail. So you can say that D8 is a subgroup of S4. So S4 has D8 as a subgroup. If you want to be a little bit more formal, it's not like D8 is inside S4, because the way we define D8 was actually different than the way we defined S4. And so D8 itself is not sitting inside S4. What we really want to say is that inside S4, there is a group that is exactly the same as D8. And in group theory, when we have 2 groups and you can relabel the elements, and if you do that relabeling, the multiplication tables are identical, then the 2 groups are the same. They might be different in other ways, but in terms of group theory properties, if the multiplication tables look identical, then the groups are the same. And the fancy word we use for that is that the groups are isomorphic. In math, we'd like to make jargon and fancy word because that makes us look smarter, and also because then we can be precise about things. Isomorphic groups is something that we will study later. So putting that all together, the best way is to say that S4 has a subgroup isomorphic to D8. And in fact, it has more than one subgroup, because instead of putting 1, 2, 3, 4 in order, you could put them in some different way as corners of the square. And then the actual elements you get are going to be different. And so you will get a different copy of D8 inside S4. And so we can say that S4 has subgroups isomorphic to D8, a whole bunch of them, that each is a subgroup isomorphic to D8. This is the end of this lecture. The next lecture will be on integers mod n with addition, as another example of a group, this time an abelian group, a commutative group. Until next time.